common mistake when I am abroad. My last name is Iezzi. First letter is I, not L. Okay, just because if later you want to send an email and you write to Annamaria Iezzi, then I will not receive it. Okay, but it's a very common mistake. Unfortunately, big I and small L, they look the same when you write it. Okay, so this is a course which is more mathematical, okay, as you will see. But I know there are many computer scientists, so I try to make a course really for everyone, okay? And you can tell me at the end how the level is going, so that in case I can adjust. But before going to the beginning of the course, I wanted to tell you a little bit more about my experience and how I landed in this field of isogeny-based cryptography. Because I didn't start from there, okay? So when I was a bachelor or a master, like many of you, I was in Italy, my country, at the Università degli Studi di Roma 3, in Rome, okay? At that time, actually my master thesis is in commutative algebra. And the title of my thesis was almost dedicated domains, okay? This was very pure mathematics, and actually I wanted something a little bit more applied. And during an exchange program in Marseille, I did a master with some connection to computer science, and this is why later I was able to go again to Marseille for a PhD. And this explains also that these exchange programs are very important for making connection and network for our career. So for my PhD, I moved in Marseille, in France, and here my topic was curves over finite fields. So what is the connection between commutative algebra and curves over finite field? Because normally when you move from a place to another, you change topic, but not so much. So the intersection point here is algebraic geometry. Commutative algebra is, is behind really algebraic geometry, and curves over finite fields, they are also in the field of algebraic geometry, but with a specified field, which is a finite field. And the title of my PhD thesis was Number of Rational Points on Singular Curves over Finite Fields. Later, I moved for a postdoc in the US, in Tampa. We are in Florida here. And this is really where I started to work in isogeny-based cryptography. So I was there between 2017 and 2020. And I started by working on this paper, Seaside, that came out in 2018. The reason was because my supervisor was working with computation of class group, and if we have the time, I will show you how this is important. This is one of the, something that appears in isogeny-based cryptography. And then I moved again because my career was, for getting a permanent position was quite long. So I found myself in the middle of the Pacific Ocean. This is French Polynesia for 1.5-year postdoc. Later, I came back to Italy, Napoli, and now finally, very recently, starting from November, I became it's kind of assistant associate professor at the University of Grenoble, which is in the middle of mountains, okay? This is just for telling you a little bit about my experience and showing you also that academia sometimes means a lot of travel, but also, this was really, as I said last time, a richness for my career and my experience. Okay, so we're going to start now with the content of this course, and I want really to say that for me participation is very important. So you will see my course many times. In my course I will ask questions which are very basic, but just to check that everyone is following. So don't be shy, answer maybe also to the most easy questions so that we can actually don't get bored, me and you, okay? And isogeny-based cryptography is normally considered one of the most complicated cryptography to start with, because as you will see, there is a little bit of algebraic geometry, number theory, graph theory. There are a lot of mathematics involved in this cryptography. But as I said, I tried to make this as simple as possible. And our main characters, it is not in the title, but are elliptic curves. Maybe you have seen this already, maybe not, but we are going really to start from there to try to understand what is an elliptic curve, why in cryptography we like to work with elliptic curves, and so on. And my main references for elliptic curves are these two books. So depending on your level, though in both there is one of the authors is Silverman. Here we have also John Tate, and this one is just written by Silverman. So this, I would say, that is more undergraduate level. And if you are looking some more advanced, you can use this book, The Arithmetic of Elliptic Curves. It is really mentioned in every paper, in every note about isogeny-based cryptography, but it's a little bit more advanced. Actually, myself, I didn't learn about elliptic curves from these books, just so you know, sometimes for a reference, but the place where I really learned about elliptic curves were the notes from the course of Andrew Sutherland, so that you can find online. And I will give you these slides. Here you have the link. And because these notes for me, they really go to the, they introduce the elliptic curves in the most basic ways. And you can really find all the proof for the results that I will not mention. So for me, this is actually the best starting point for people that want to learn about elliptic curves. Okay, so let's stop for a moment here, and you will see I will do my course a little bit on the board, and a little bit like the main will be on the board, and something will be on the slide, the pictures and things like this. So this is the first time that I try this. Let's see how it goes. Okay, so we will start from the definition of an elliptic curve. Oh, maybe this is not a good. Okay, yeah. We will start from the definition, the definition that is given in an algebraic geometry course of an elliptic curve. So this is a difficult definition if it is the first time that you see it, but we are going to make it simple. Okay? So definition. I write it and then we comment it together. I suggest you to take notes because I'm not sure that I will have time to write this I will be able to share this. So I suggest you to take notes, and again, I will give you all the references about where to find material about this. Okay, so let K be a field. An elliptic curve that normally we denote by E for elliptic over K is a smooth projective algebraic curve of genus 1 defined over K with a distinguished K rational point that we denote OE. Okay, so first of all, how you can see we work over a field. Do you have any example of a field? Which field do you know? Sorry? The reals? Complex? Rationals? FQ? Okay, so these are the most standard examples, okay? So now we want to try to understand this definition, okay? So we are going to start from the easiest example of curves. So what are the easiest examples of curves? Yes, but so normally where we draw them on a plane, okay? So these are, let's try to understand. This is the question that I have here. We are going to understand which plane curves are actually elliptic curves, okay? Okay, so can you make some example of elliptic curves or plane curves? Plane algebraic curves? An example? Sorry? Parabola, so how do you define this algebraically? I didn't understand? Okay, we normally, like this is good? Okay, but it's the same x equal y square, of course. Okay, another example? Yeah, straight line, how you define this? Okay, and normally we take, where do we take these coefficients? Over R if it is if we're working with real numbers, okay? So do you see that, of course, these are not all the kind of curves that we can describe, but when we talk about algebraic curves, we're talking about polynomials. So what is the polynomial that is behind this curve? Yeah, I can bring one in an aside, so it's y minus x squared, okay? This is y, okay? And here I can do the same thing. My polynomial here in two variables is y minus ax minus b, okay? So let me give you now more precisely what is an algebraic plane curve. So definition, an affine plane algebraic curve. Then let us denote it C for curve, defined over K. Is defined by a non-constant polynomial in two variables, so it is f of x, y, with coefficients on the field where we are defining our curve. So this denotes the ring of polynomials in two variables. Okay? So our curve, it is defined as the zeros of this polynomial. So our curve C is defined with the equation f of xy equal to 0. Okay? So we did already some examples. I'm going to remove this because I think that is worse. Okay. I will explain you later. Yes, but good question. Good question. Okay, I'm erasing the definition, but we keep it here on the slides. Okay? Okay, so something very important to understand in algebraic geometry is that when we define a curve. The curve is defined over k. It means that the coefficients of our polynomial are in k. But when we look for the points, we have to go to the algebraic closure of k. Okay? So let us recall this. We denote k bar, let k bar be the algebraic closure okay. I don't know if you have ever heard about this. Does someone can tell me what is the algebraic closure of R? C. Is it true that the algebraic closure of Q is equal also to C? Why not? Is there an element that is in C but not in the algebraic closure? Which is this element or those elements? I don't know. There are several examples. Pi. So this is different because pi is an element that belongs to C but not in Q bar. And why it does not belong in Q bar? It's not a root of a polynomial with coefficient in Q, right? Okay, so you see, basically taking the algebraic closure is basically taking all the roots of the polynomial that we can define over that field, okay? And you will see that also for finite field, we have an algebraic closure that we denote like that, and is again the set of all roots of all polynomials that you can define over FQ, okay? So why we talk about this algebraic closure? Because when we do geometry, okay? When we do geometry, we consider points with coordinates in the algebraic closure. This set is denoted by C for the curve and in parentheses K bar. So this is the set of points x, y. Here it denotes that x and y are in K bar. That verifies the equation f of xy equal to 0. Okay? This is something important to understand and to keep in mind. But when we do arithmetic, we are allowed to consider points which have coefficients just in our field K or some other field that contains K. Okay? So this is denoted by C of K, and it can be defined the same way. We just replace K bar by K, and this is the set of xy belonging to K such that f of xy equal to 0. This set is called the set of K rational points. Set of K rational points. And you see here, it is called standardly rational because at the beginning they were looking for solution over the rational numbers. But then it has been generalized to any field, finite field, I don't know, R, whatever, okay? Okay, so already now we are working with plain affine algebraic curves. What we have to understand is what it means for a plane curve to be smooth, okay? Maybe you know this already, but let us see it together. So definition. So imagine our curve is defined by an equation like this. This curve is smooth if and only if we can define by using derivatives, okay? So the partial derivative of f in the x computed in the point xy, and the partial derivative of f in the y computed in the point xy is different from 0, 0 for every point xy belonging to for every point of the curve, so with coordinates in algebraic closure. Okay? So this is the definition. Let's make us an example. Let us make an example of a curve which is not smooth for understanding this definition. So my curve is defined by the polynomial f of xy equal y squared minus x cubed. And so my curve is the curve defined by the equation y squared equal x cubed. It looks like this one, okay, over the real numbers. So would you like to say that there is a point where this curve is not smooth? The origin, because basically when you draw the tangent line, at some point you have to jump, okay? But let's make this, understand this with this definition, okay? So let us compute the derivative, so the f in the x and the f in the y, okay? What is this for this curve? The partial derivative in x? Minus 3x squared. Do you agree with me? Yes? And the partial derivative in y? 2y. Okay? And we are asking for the points that makes this equal to 0, 0. The points of the curve which make this equal to 0, 0. Which are? So if and only if xy equal to 0, 0. Okay? So 0, 0 is the only singular point on this curve. Okay, well, we have understood a little bit better what it means smooth. Let us now try to understand what it means to have genius 1. Any question? Yeah. In which sense? With the tangent line. The tangent line. You know, here
you will find there are 5 elements in that entire Grenoble basis. So starting from 2
as a slope, and at some point, for moving to the other tangent line, you have a jump in the value of the slope. Okay? It is clear what I mean? But we will do later other examples. Okay? But it's also considered a singular point, yes. But which example you have in mind? Well, but this is, okay. Yeah, it has to be defined by a polynomial anyway, okay? And polynomial are continuous functions, right? Okay, so let's go back to the definition. Oh, this I don't know why I put it here. Ah, no. Okay, here's the definition. Okay. So let's try to understand what it means now that our curve has genius 1. So this is a fact. So let us consider a polynomial f of xy with coefficient in k of degree d. Okay? So what you have to remember is that if the curve C defined by f of xy is equal to 0 is smooth, then there is an easy way for computing the genius. then its genius, that I'm not able to define in this curve because the definition is very complicated. So its genius is, we compute very easily starting from the degree. D minus 1 times D minus 2 over 2. But this is true only if our curve is smooth. If it is singular, like in the previous case, we cannot compute the genius like that. The singularities make the genius different. But let us imagine that our polynomial of degree D defines a smooth curve. We're interested in curves of genius 1. Okay? So my genius has to be 1. And by this fact, this means that this quantity has to be 1. So D minus 1 times D minus 2 over 2 equal 1. Okay? We have to solve this equation. Okay, I did some computation for you, so very easy computations. So when I solve this, I get the polynomial D squared minus 3 D times D minus 3 equals 0. Okay? So what are the degrees that make my curve of genius 1? So by solving, I would say D equals 0 or D equal 3, right? Why we shouldn't consider D equals 0? The polynomial was not constant, okay? So we have to look for, if we sum up what we got so far, we have to look for affine curves which are smooth by following this definition, and whose degree of the polynomial is equal to 3. I will write this here now. So, my curve defined by a polynomial fxy equals 0 is an elliptic curve if and only if the following things are true. So, first of all, the fact that it has to be smooth, so we translated this that the system with equation f of xy equal to 0, the f in the x calculating xy equal to 0, and the f in the y of xy equal to 0. What are we asking for this system? Does not have solution, donc has no solution. Where? In k bar squared, okay? Geometry, so algebraic closure. Okay. What is the other condition that we saw? The degree of f is equal to 3. Okay, and this is not enough. You will see why. I'm not telling you nothing now, but here we have to put something else. Okay? Again for you, let us try to say whether our curves are elliptic curves or not. So, is this an elliptic curve? No, it is a line. What is the degree? 1. Okay. Is this an elliptic curve? No. Why? It's 2. Is this an elliptic curve? We saw it already. Why not? But it has degree 3, right? So no smooth. What about this one? Well, when there is a self-intersection, this kind of singular point is called knot, okay? So 0, 0 is a singular point. You can do the computation and check, okay? So this is not an elliptic curve. What about this one? I agree with you that I would also like to say that this is an elliptic curve, right? But I told you that I'm missing here one condition, okay? This is actually not an elliptic curve, because from an algebraic point of view, an algebraic geometry point of view, this is like a line, okay? And what is the problem? It is true that it is not smooth for, you know, from like an affine point of view, it is smooth, sorry. It has degree 3. So what is the problem? The problem is this last adjective, projective, that I didn't mention so far and which is important. So the previous curve is smooth everywhere apart what we call points at infinity. So it has a point at infinity, and at that point it is singular. So in this course, I'm not able to tell you exactly what is a projective curve. You know, it takes so much time, and we don't need it really. If you are interested, you can ask me later this evening in the exercise session. But keep this in mind that actually we have also to make sure that our curve has the points at infinity are non-singular. Okay? So let us see some examples of elliptic curves, how they do look like. Yes?
So in the last line of the slide, moving between G equals to 1 double implies G equals to 3, right?
Sorry?
Is that really double implication? So is double implication for both ways? If D is equals to 3, doesn't G equals to always 1?
These are double implication because I'm just solving the polynomial, right? What is, of course, you know, D equals 0 also, but we are assuming that our polynomial is non-constant. No, am I wrong?
No, I think the answer is D is equals to 3, is always 1.
For a smooth curve.
So
Yes, for a smooth curve, yes. Like a smooth curve from a projective point of view, okay? Yes. If the curve is non-smooth, then you cannot calculate the genius like that. Okay?
Thank you.
Okay.
If only fxy equals 0 has no solution, then...
Why we have this equation?
Yeah.
Because you can have sometimes that these two are 0 at some point which is outside the curve. And that is not interesting to us. So the point that makes it 0 has to be points of the curve.
So you mean all three together must not be 0?
Yes, exactly, exactly, the system. Okay, so let us see some examples of elliptic curves. So this is an example of elliptic curves, y squared equal x cubed plus 1, y squared equal x cubed minus x. And these are all examples that I'm showing you over R, okay? Why I do that? Because so that we can represent them with, you know, on the plane very easily. Well, because if you compute the tangent line, this is smooth at every point. We can actually do the computation if you want. The fact of having two, like, and always you have to consider that we are looking at it over the algebraic closure, which is C. Okay, so this is the set of rational points. Okay? Three real root, right? Yes. Only one real root, yes, and the other one are complex. So they also define points. So, you know, like here over the only point, so you have that, what is that? 0, minus 1. Minus 1, 0 is a point with y coordinate equal to 0, but then you have also, you have I and minus I 0, okay, as a C rational point, okay? Perfect. Okay, what I have later? Nothing. Okay, so the last two examples were, so this I did. Okay, so we saw that two examples are, I'm writing them here as well, so y squared equal x cubed plus 1, and y squared equal x cubed minus x, okay? Okay, so these two examples are particular cases of the following form. So, of the form y squared equal x cubed plus ax plus b, with a and b defined over our favorite field. Okay? So the question that we are going to answer is this an elliptic curve for every value of a and b? So is this an elliptic curve? For every value of A and B, for every A and B in K. Okay. So, first of all, with respect to what we said, what is the degree of this polynomial? 3. So this condition is checked, okay? Then you have to trust me that this curve is also, this kind of curves are non-singular at the infinite point. We will try to understand later what is this infinite point. So non-singular at the infinite point, the point at infinity. Okay, there is only one point at infinity, and we'll see that this is denoted by, for this curve, it is, zeta, 0. Okay, well, but we will come to this later. No, for now, just trust me. And then what we have to check? We have to check that system, okay? Let us say together what are the 3 equations of the system. So the first one was f of xy equal to 0. So what is here? Y squared equal x cubed plus ax plus b. Okay. What is the second equation? Sorry? Three x squared plus a equal to 0, right? And the last one? 2y equal to 0. Okay. We have to solve this system. What would you do here? Y equals to 0. Just a precision. Here we assume that the characteristic of our case field K is different from 2 and 3, okay? Because otherwise here we would get, and this is important, sorry. So y equal, do you agree that this is equivalent to say x cubed plus ax plus b equals 0 and 3x squared plus a equals 0, right? What is this equation, this polynomial for the first one? So we're saying that the polynomial in one variable, x cubed plus ax plus b, and the polynomial 3x squared plus a have a common root. So if and only if the polynomial, so when a polynomial and its derivative in one variable and its derivative are both equal to 0, it means that the polynomial has a double root, right? So has a double root. What is something that captures this information? For a polynomial of degree 2, when this is true? Sorry? Self? No, not exactly. What? Because these are two different curves, okay? But for instance, for a polynomial of degree 2, what number, what quantity capture? Yes, if the discriminant is 0, as the polynomial has a double root. And here is the same. So, but you have to know what is the discriminant of this polynomial. And for this particular kind of polynomial, there is a formula, you know? Ah, you are very good. Okay, so if and only if minus 4a cubed minus 27b squared is equal to 0, okay? So what we have seen, that if this quantity is 0, my curve is not smooth. It has a singular point, okay? So this is why, actually, we have to, here, the answer to this question here is only when 4a cubed plus 27 b squared equal or different from 0? Different. Okay? So, if I sum up what I said, y squared equal x cubed plus ax plus b, with a and b in k, and this quantity is different from 0, is an elliptic curve defined over K in, so this is called short bias transform. Okay? So, just to sum up what we said. Okay? So when you read a paper in isogeny-based cryptography, they will not tell you all this, okay? They will just start, let y squared equal x cubed plus ax plus b, an elliptic curve, okay? I wanted to explain what there is behind that, first of all, and now I'm going to tell you why we cannot actually just restrict to this easy formula for an elliptic curve. Again, something that we don't have time to to show, but that you have to keep in mind, is that if K, so let K be a field of characteristic different from 2 and 3. Okay, these are very specific cases where there is also an easy form that you can find in whatever book of elliptic curves. But it's just in isogeny-based, we are not interested to these cases because our characteristic P will be very, very large. So why we should care for P equal 2 or 3? Okay. So let K be a field of characteristic different from 2 and 3. Then every elliptic curve defined over K is isomorphic to an elliptic curve in short Weierstrass transform. Okay? No, so something like that. I didn't tell you what it means to be isomorphic, okay? But also this we will see later. But imagine that we are interested to elliptic curves up to isomorphism. It means that you can always choose our favorite form, for instance, for instance this one. Okay. Affine because it is not projective. So if you want to make this projective, you should obtain from this a homogeneous polynomial. Okay. So you basically have to multiply by z in a way that this becomes every term becomes of degree 3. So the projective form will be y squared z equal x cubed plus ax z squared plus b z cubed. But if you've never heard about projective geometry, this is complicated to understand in 5 minutes, okay? It's just that for us it's very easy. Now we will make the point that this curve has the points that satisfy this equation plus a distinguished point, which is the point at infinity, okay? So our curve E will be something like this. Okay, and like we did for any curve, we can do also for an elliptic curve. We can consider the points from a geometric point of view over k bar. So this will be, in this case, the xy in k bar square, such that y square is equal x cubed plus ax plus b. And we can consider the point over k, okay? So the xy in k square, such that y square equal x cubed plus ax plus b. So here is very nice to do an example. Okay, I take an easy curve E, something of the form we saw already, y square equal x cubed plus x over F3. Okay? What is F3? the finite field with 3 elements, which are 0, 1, 2. Okay? And I don't want to write, to list A as 3 bar. Why not? Well, this set, how many points it has? Infinite. For every value of x, and I have infinite possibilities here, I have 2 values of y, okay? 2 or 1, depending on the case, but at least 1, okay? So this is infinite. But what we can do, actually we are going to do now together, we can list what are called the F3 rational points. How are we going to do this? So we have couples. How many you have at most? Oh, sorry, but still, true, but still we can do this. And this is an elliptic curve, okay? You're right, but so when, you know, what is not true for characteristic 3 is that this an elliptic curve, whatever elliptic curve is isomorphic to this form. But this is still an elliptic curve, okay? Sorry. Actually, you know, because this condition is true. What was the problem is it was the 2 in our derivative, right? Okay? So this is still true in this case. So let us list the points. How do we do this? Well, was not a very good example from my side. It's true, but I wanted to make calculation easy. That's why I chose F3. Maybe I would have chosen F5, but okay. So how are we going to list all these points? For instance, if x equal to 0, 0. Okay, then I have to do something here. Okay, 0, 0. Then if x equal to 1, this becomes 2. Do we have an element in F3 that when we square we get 2? No. Okay. So for 1 we don't get anything. What about 2? From 2 we get 2 cubed here is 8, plus 2 is 10, so is 1, and so we have 1 and 2. Okay? And here is important, I forgot something very important. This is not all, because we've always to add our point at infinity that we denote 0e. Okay, so here, union, our points at infinity. Okay? So even if you do not understand what is that, it is always there. It is a point which is actually our distinguished point. Okay. Now we're going to understand why actually elliptic curves are very important for cryptography. What is a characteristic of elliptic curves that makes a difference compared to curves of genus 2, 3, 4, etc. Okay? So what happens is that we can define an addition law on the set of points of my elliptic curve. Okay? and also on the set of rational points. Okay? This is defined in a geometric way. Okay, so let us understand this group law that somebody already mentioned in a talk, in one of the student talks. So imagine that we have a curve, an elliptic curve, for instance like this, okay? Let me do actually this a little bit different so that we can see better. Okay? Well, we have to define an addition law, so something that goes from the Cartesian product. So here takes 2 points, basically, and returns another point. P plus Q. Okay? We want to see how this is defined. And how, in the same way the student last time told you that you don't have to sum the coordinates pairwise. Okay? The construction is different. It is geometric. You take 2 points, P and Q, on your curve. Okay? You draw the line that passes through these 2 points. Why do we get a third point? Why are we sure that we get a third point? Because this is a cubic, degree 3. When we intersect with a line, we get 3 intersections. This is Bézout theorem, okay? So we get this intersection, but we don't take this as the sum. We actually take the symmetric of this point, okay? So I repeat, take 2 points, draw the line, I find an intersection, I take the symmetric with respect to the x-axis, okay? Because these curves of the form y squared equal x cubed plus ax plus b are always over the real numbers symmetric over about the x-axis, okay? And the same way, well, I can do it also in the same picture. We don't have colors right here for the chalk. Okay. Oh, in the same way, if I take another point here, P1, how would I add that point to itself? I take the tangent line, right? And I find another intersection. Again, I don't take this, I take the symmetric. This is 2P1. Okay? Of course, we want that the set of points together with this addition law verify some properties. What are these properties? It is commutative. Of course, the construction is the same, so it's commutative. Then it is true also that it's associative, but it's more difficult to prove, okay? Associative. Again, go to one of the books if you're interested in it. And then it has a 0 element, like identity. And in your opinion, what is this identity? The point at infinity, okay? What it means that you have to imagine this point at infinity really at infinity, okay? You take a point, you draw the line, you find another intersection on the same y-axis, and you take the symmetric. So this doesn't change. So it verifies that 0e plus p equal p plus 0e equal p for every p. Okay? And then, sorry, I put it here. What is the last one? For every element there is an inverse. So for every p, there exists minus p such that minus p plus p equal my identity. In your opinion, what is the minus, I don't know, minus p1? It's just taking actually the same metric, okay? Because these two basically, they add to infinity. Okay. Sorry, here was a little bit not well written, but what is important for us is that actually AK bar and also EK are abelian groups. Abelian is for commutative, okay? And on this thing is based what we use nowadays, which is the Diffie-Hellman key exchange, elliptic curve key exchange. I would like to know if there are some questions so far. Still get a third intersection with coefficient in K. Actually, we are working over R here, which is not algebraically closed, and still you get a third intersection with coefficients in that field.
Yeah, that's what I'm not able to visualize. It's clear it's an EK bar, but why will the sum of 2 points in EK also lie in EK?
Because basically, also the line is defined over K, and the third point has necessarily to have coordinates over K. There will be an exercise on this afternoon, and you will understand this better, okay?
Also, one more thing. So in this case, we are taking K to be R, a real number.
Here, K is R.
So if it was a finite field, then it would be kind of discrete. So
wait, this is very interesting. Now I will show you something, okay? Actually, you can a little bit rest. You don't have to take notes because we are going on the slides for a while, okay? So, over R. So we saw this additive law. We take 2 points. I do it again. I draw the line, intersection. I reflect the intersection. This is my point. Okay. What happens over a finite field? In your opinion, how does this look like over a finite field? This it, like points, right? Let us visualize this. Here we are over F47. My curve I took this because I wanted to take the same if it was nice. So y squared equal x cubed minus 2x plus 2. Okay? Now I will show you something that actually no one ever showed to me, and it is really interesting because you can see the additive law also here. Okay? I made this when I wanted to do a presentation. I wanted really to see if over a finite field we could still see the group law. So let's take, first of all, you notice that there is also a symmetry with respect to this axis. Because what does it mean? Because if we have y, xy, which is a solution to something, also x minus y will be a solution. The only thing is that y minus y here are points, are numbers such that their sum is 47, okay? In an elliptic. Okay, so let us take 2 points here. My point P is 1129. My point Q is 1225. They satisfy this equation. And now I would like also to draw the line. Okay, I draw the line. I arrive at the end. What do I do in your opinion? Now, can I keep going with this line? I didn't find an intersection, you see? Can I keep going? Well, what I have to do is like in this game where the character goes away from the bottom and where it reappears? In the top. Okay. Did we find an intersection? Not yet. Oh, again, we find it. So this is our unique third point, because we cannot have more. Is it our sum? No. Take the symmetric with respect to the x-axis. So P plus Q is, you see, it's not the sum of the coordinates. It is actually, it is to be defined in this geometric way. Okay, so we have this group. Let's see, first of all, so today I think that I will not be able to go much farther away, so we will keep this for next week. But let's understand already how nowadays elliptic curves are used in cryptography. So there was this breakthrough in 1976 when Diffie-Hellman proposed a new protocol for key exchange. Okay? Their protocol was not using elliptic curves. It was using Diffie-Hellman key exchange was using the multiplicative group Fp star. So what is the multiplicative group? You take a prime number P, and you can consider the invertible elements with respect to multiplication. So 1, 2, until P minus 1. Okay? And it is easy to check that this is cyclic. So there is a generator. So there is an element that if you keep taking powers, multiplying by itself, you actually recover all the set. Let us make an example. If I take F11 star, so 1, 2 until 10, I can show easily that 2 is a generator. Okay, this is not the clock with 11 hours. It's just for showing that if I take 2 and I multiply by itself, I get 4. Then if I multiply by 2, I get 8. Then if I multiply by 2, I get 16. So modulo 11, 5, 5 to 10, and etc. Keep going. I basically land in every point here. So this is a generator. So how do you use this? For Alice and Bob here, they want to arrive to the same key, to the same secret at the end. What do they do? Here, imagine that in the middle there is Eve, who sees everything that is transmitted over the public channel. Okay, so in the black part, everything is public. So what we have public here? The prime P, which is large, and a generator G of our multiplicative group. So, and everything you have in the blue part and the orange part, they are secret respectively to Alice and Bob. So Alice, she chooses a number between 1 and P minus 1, an integer, okay? And she computes G to the A. She sends this through the public channel. And the same does Bob. Bob chooses B, an element, one integer between 1 and P minus 1, computes G to the B, and sends this to the public channel. So what an attacker can see are big A and big B, okay, which are respectively G to the A, G to the B. Then Alice takes B, what he received from Bob, and she raises to the power of A. So she's computed G to the B to the A. And same thing Bob, he computes A to the B, which means G to the A to the B. But multiplying G itself B times and then A times, so these two elements are actually the same, and so they get secretly their key, which is G to the A to the B, G to the A times B, okay? And from the point of view of an attacker who just sees big A, which I remember is small g to the small a, and big B, which is g to the small b, our goal is to recover the secret key. But basically, if either they have small a or small b, the game is done. And this is exactly what is called the discrete logarithm problem. So for instance, given G to the A, compute A. Okay, so FP star is just an example of finite abelian group. And more in general, this can be done with any finite abelian group. We have just to make sure that something works well. So first of all, we want that it is easy to compute this power G to the A. So this can happen in polynomial time. And on the other side, we want that the discrete logarithm problem is difficult, so that it's difficult given the generator of the group have an element of the group to compute the power A. Okay? So we are interested in groups that are finite abelian group with these two properties. Actually, this is called a one-way function, something that is easy in one way and difficult in the other way. Okay? So we need a little bit of time. You see that now this would have gone much faster. We were in 76 and we are here in 85, 87. It's a long time because you have to imagine that elliptic curves were very well studied, the properties were known. And independently, these two researchers, so Victor Miller and Neil Koblitz, they discovered the use of elliptic curves for Diffie-Hellman key exchange. So I made this just as an example here. The most important key thing to remember is that our law is additive, okay? Not multiplicative. So it sounds like slightly different. What is public here? We have a finite abelian group. So let's take, for instance, this curve, the previous one, over F47. Let's fix a point of this curve, okay? This is a point here of order 11. It means that if you add 11 times, you get the point at infinity. So what happens here? Well, as before, Alice chooses a secret, an integer between 1 and the order of the point, for instance, 7. And she computes now what was G to the A, now is 8 times the point, because the law is additive, and sends this through the channel to Bob. And Bob does the same thing, chooses the point 9, computes the integer 9, computes 9 times p, and sends it to Alice. But this group now, this law is commutative, so when Alice computes 7 times the point received by Bob, and Bob does the same with the secret 9, they get basically the same thing. Here, these computations are done are not very easily. They are done with Magma or some like math software. Okay, so they get the same secret here, which is the point 36.3. And so again, from the point of view of an attacker, the goal is given p to compute the integer a, such that when we multiply a times p, we get, for instance, 914 or 1932. Okay, I want really to make this real, because this is actually what is used in WhatsApp, and I learned that Indian, like Italian, you love WhatsApp, okay? We are the same in Italy, okay? So WhatsApp really uses elliptic curve Diffie-Hellman for key exchange, and you can see that on the documentation of WhatsApp. And they use a particular elliptic curve, a curve which is called 255-19, and you will understand why. So in elliptic curve cryptography, you see, you fix one curve, you work on a given curve. So this curve has to be well chosen in a way that the discrete logarithm problem is difficult. So here the public parameters are this curve. So far nothing to see with this number, okay? You can tell me, but you told me so much about curves in short bias transform, and then this is not in short bias transform. This curve is what is in a form which is called Montgomery form. And this is a form which allows fast computation, fast multiplication like for computing a multiple of a point. This is much faster if the curve is given in this form. So there are different kind of forms for elliptic curves. And then we work on the prime P that explains is a prime of 255 bits, and it's very long, okay? So you see very big primes. And also you fix a point, and also the point is given. It's the point with x coordinate 9, y coordinate very ugly, okay? And so with these fixed parameters, you every time, I don't know now exactly because I'm not an engineering, so every time that you establish a connection of WhatsApp, what secure your end-to-end encryption is this kind of curves. Okay, then we've seen this already. What happened in 1994? We had the Shor algorithm. This is a quantum algorithm, and the problem of this algorithm is that computes the discrete logarithm problem on an hypothetical quantum computer in polynomial time. And you see, in the same line where we have like some technological progress on algorithms for computing, for solving this problem, now that we have quantum computer, we start having also like progress for building big quantum computers. So the first working 2-qubit was built in 1998. And so basically then there were some improvement also on the side of quantum computer at the point that on 2015, the NSA announced that it is planning to transition in the not too distant future to a new cipher suite that is resistant to quantum attacks. And this didn't take too much time because in 2016, the NIST, which is National Institute for Standard and Technology, launched the post-quantum cryptography competition. In 2019, there are several companies that are working on build quantum computer. One of the most famous one is IBM, Google, Amazon. In 2019, we have the 53-qubit quantum computer. And then now I don't know where we are, but you can see a progress from both sides, quantum computer and algorithms that resist to quantum computing. So what happens now is that now we are not going to work anymore. If we are in the post-quantum setting, we cannot work anymore with a given elliptic curve and with this addition law, because this is broken by Shor algorithm. So we cannot use this, not even other finite abelian groups, okay? They are all, the discrete logarithmic problem is broken on all finite abelian group. But what we are going to do, we're actually going to work with a set of elliptic curves, okay? This set you will see is very big, like with very prime number, this will be, this number of sets is exponential, okay? And actually we are going to work with connections between these elliptic curves. So these connections are nothing but what we call isogenies. They are maps between elliptic curves. So again, we don't fix a curve and we work with each set of rational points. We take a set of elliptic curves and we work with these maps between them that are called isogenies. So the time is almost left. I will just give you, I don't know, maybe it's also, okay, 7 minutes, how much time? Okay, I will do the finish in 7 minutes and that we will do examples next time, because I think it's good to finish by giving the definition of an isogeny.
That was the rational points or was it almost?
Sorry?
The F47 which you had shown, that figure.
Yeah.
That had only the rational points?
These are all the F47 rational points, so you cannot see them like the other points. It is possible to draw this on a plane because, you know, these finite fields work a little bit different than real numbers. But until we are working with integers between 0 and 46, we can represent those on a plane like we did with this discrete set of points.
So the actual elliptic curve will have infinite many points? the actual elliptic curve, but this was only the rational point, so
Yes.
that is finite.
Otherwise, it has infinite point over the algebraic closure. Okay, but we cannot draw them.
So in cryptography, we only use the rational points. We don't use the.
Like not in general, elliptic curve cryptography, so also isogeny-based cryptography. The good thing of using rational points is that they are more efficient. But you could use them if you could use also non-rational point defined over a quadratic extension of the field. You know, it's just that you try to use the parameters in a way that is more efficient to do computation. Okay. Okay, so let's finish it with by defining what is an isogeny, okay? Like for elliptic curves, I'm going first to give you the difficult definition, but next time we're going to make it simple. I don't think that I will have time today. So what is an isogeny? Definition. So let E1 and E2 be two elliptic curves defined over a field K. An isogeny normally denoted by phi from E1 to E2 is a non-constant